we have another conservation law we have to take a look at here. This one involves momentum. Now we've talked a little bit. Let me choose a good color up here. There we go. We've talked a little bit about momentum so far. Now that's the product of the mass and the velocity. And this quality can be described as maybe the quality of motion an object has. Maybe it could be a number to describe how difficult it is to get something to stop. An object with either no mass or no velocity would be very easy to stop, either because it puts up no fight to the reduction in speed or because it's already stopped. Now, this quality holds something very similar to the qualities that energy has, and that is the fact that once you have a certain amount of it, that amount remains constant. If we take a certain situation, this is supposed to be a box, where you have objects moving around. One object maybe flying to the right, another one going down and to the left. There's a certain amount of momentum encompassed in each one of these objects. The momentum of the first one over here, and this object here also has a certain amount of momentum. These can be calculated independent of each other. In other words, if we want to find the momentum of this object, just takes its mass times its velocity, and then to find the momentum in this one, its mass times its velocity. Wonderful. Now, what happens to these two objects if they ran into each other? What would happen to the total momentum of these objects? There's a reason I've drawn a box around these objects here. I've declared something I call a system. And we did this occasionally in energy, but it wasn't quite as important there as it will be here. Right? This closed system here means anything happening on the outside of it has absolutely no impact on what's happening on the inside. If you can declare a certain situation like this, then the total momentum of these two objects will remain constant. In other words, if you take this momentum here and you add it to this momentum here, whatever happens after the collision, the total momentum of these two objects remain constant. If we take the momentum of the first one and add it to the momentum of the second object, this here will be a constant. Now, this is similar to something we talked about in energy. With energy, we said that the total energy that's in a system initially is equal to the total energy after something happened or any time later. Conservation of energy. We even looked at a specific instance of this where the mechanical energy of a system was constant. The mechanical energy you start out with, the mechanical energy you started with was equal to the mechanical energy you ended with, or the initial and the finals are equal. These are all conservation laws. Here, we're going to be dealing with the same thing again. The universe has a way of conserving certain qualities. There's nothing magical about the universe in physics. Everything that happens for a reason. The law that dictates momentum is the conservation B-A-T-I-O-N of momentum. And this is an extremely classical law in physics. As far as you go into studying physics, this law keeps coming up and up again. And all of it falls down the same line as all the other things we've looked at, all the other conservation laws, conservation of mass, conservation of energy. The amount of momentum you start out with this situation is the amount you end with, or the final. Now, you have to be very careful in declaring the situation that you're dealing with in these cases. For instance, if I take a ball here and I fling it down to the ground, it starts with a certain amount of velocity, initial velocity. Okay. If it bounces off the ground, this thing will be coming up at a velocity like this, up away from the ground. Right. The mass of this object, we can see in both cases, is going to be the same. But the velocity has changed. If we were to calculate the momentum initially, it would be different than the momentum final. Well, where did this momentum go? Much like energy, if momentum is conserved, then it had to have gone somewhere. In this case, a problem arose because we didn't classify our system. When you classify your system, you have to take into account everything that's interacting with each other. Here, we have the ball interacting with the Earth. So the situation, or what would I call these? The situation you're dealing with is one that involves the ball and the Earth. The momentum initial was not only in the ball. The Earth has a certain amount of initial momentum as well. If the total momentum of the ball has changed, and it happened because it collided with the Earth, the momentum that the ball changed with had to have come from the Earth. That's right. Even when you take a ball and you throw it down towards the Earth, you're actually changing the momentum of the Earth. But this is a complicated situation. Let's deal with more simple situations initially. Objects traveling in one direction. I'm going to take a car. They're much more interesting on the dry erase board. I haven't got quite the hang of this thing. These look like nothing. Why do all my cars look like hats and eyeballs? I don't get it. Anyway, a car traveling to the right, let's say at 5 meters per second. Another car traveling to the left. Here's a car. Here's a car. Good. Also traveling at 5 meters per second. Both these cars will even give the same mass, 1,000 kilograms and 1,000 kilograms. Right. To understand the conservation of momentum, we have to first be able to individually measure the amount of momentum each object has. Well, that's fairly simple. It's just the mass times the velocity. A common mistake we make in physics with dealing with velocity is to include the direction into it. One of the first things we studied was velocity, and we said it was a vector because direction is very important with it. This is not more evident anywhere than it is here with momentum. We have to declare one direction as positive, one as negative. And it's always just as easy to pick to the right positive and to the left negative as anything. So this object here is traveling to the right with a positive velocity. So its momentum would be 5 meters per second times 1,000 kilograms equals a positive 5,000 kilogram meters per second. Awkward unit for momentum, remember, kilograms, meters per second. And that's the momentum for the first object. Object 1, object 2. Okay. Now, we have the second object here, which also has this momentum. Its mass, 1,000 kilograms, times its velocity. But remember, since its velocity is in the opposite direction, it is negative. The momentum of the second object equals negative 5 meters per second times its 1,000 kilograms equals a negative 5,000 kilogram meters per second. All right, so let me see if I can get myself a little bit more room here. Nope, I'm about out. Now, think about the total amount of momentum in the system. I've said that our system is everything close inside this box. Nothing from the outside is affecting these two objects in any way. No forces, no energy exchange, nothing. The total momentum in the system is nothing more than the sum of the two momentums. In other words, the momentum from object 1 plus momentum from object 2, that is the initial momentum. Okay. And what does it come out to? Well, you can probably think about that real quick. The momentum from the first object is 5,000. I'm going to drop the units, just saves a bit of time, plus the momentum from the second object, negative 5,000. So what's the total momentum initially from these two objects? 0. If you were to observe these objects from the outside, and even though they're two objects, if you thought about them as one object, you could think about it as one object with a total momentum of 0. And this is what the situation starts out with before the collision. I said collision. The nice thing about momentum is when we finally start getting to slam things into each other. If these cars did collide, what would happen to them? Well, they're two cars of the exact same mass, traveling in opposite directions at the exact same speed, with exact opposite momentums. And furthermore, they start out with the initial momentum of 0. The conservation of momentum law says that whatever momentum we start out with is exactly the same momentum we have to end with. So the final momentum of the system has to be equal to the initial momentum. And if the initial momentum is 0, what's the final momentum have to be? So, what's going to happen to these objects most likely? Well, one of a couple things could happen. They could come back together, collide, and stick. We're going to know this type of collision here as which one is it? An inelastic collision, where the two cars stick together as a huge mass of steel, where their total velocity is 0. Their mass might be doubled due to the fact that there's two cars stuck together, but the velocity of 0 will indicate that these have a momentum of 0, which is allowed by our conservation of momentum law. Well, instead of them sticking together, they could also bounce off each other, where objects would be going in opposite directions. A smashed front of a car. I know it doesn't look really any different than my normal cars. And a smashed front of another car. Now they're starting to look more like spaceships. Traveling in opposite directions. Well, if they still have this initial, or I'm sorry, not initial, this mass of 1,000 kilograms, 1,000 kilograms, right? And they're traveling in opposite directions, the total momentum still has to be conserved. It still has to be 0. Well, how do we find the final momentum? Well, let's just see the momentum of each of these individually added together. The momentum of object 1 and the momentum of object 2. Okay. This one here is 1,000 kilograms. This one here is 1,000 kilograms. Hopefully you can see that the only way for that to be possible is if these two cars' velocities were identical. If you can't see that, that's okay for now. But we do have to understand that the initial momentum that we started out with has to be exactly equal to the final momentum. Alright, there we go. Take a quick minute break. We'll get started on the second video in a second.